Hello, everyone. Hi, welcome to our session. There is a little problem because Giovanni has problems to get through, to find a Zoom link to our session. So before he joins, let me tell you a little bit about these 3 days that we are going to have together. We have 5 talks. We have 5 talks today, including mine. I took the liberty to have my talk to schedule my talk right after this welcome speech. Just that you might have enough of me after that. So today we have 5 talks of people from North America because the morning is not very convenient for them. So today we have all our friends from North America. Tomorrow we have another 7 talks, and on Wednesday the schedule. There are 5 talks in schedule, and then after that we'll have a talk by Jose Manuel Carmona, who will tell us a little bit about physics and a little bit about cost action, right, Jose Manuel? Oh, okay.
Sorry, yes.
And
right,
then
yes.
after this talk by Jose Manuel, Giovanni Amelino Camelia, who is a co-organizer of this session, will give a session summary, and he shares some thoughts about quantum gravity phenomenology as far as understood what he wanted to tell us about. I have some. I had some requests concerning changing the slots, and I did what I could. I got another request today, and unfortunately today I cannot really do anything at this moment. So if any one of you really wants to exchange slots with somebody else, please try to contact this person directly. And then if you agree to exchange slots, please let me know. Are there any questions that before we start? Is there? You can unmute if you want to say something. All right. So if there are no, okay. Each of you have time for his or her slot, and this time, as I understand, it's clear, includes also question time. So the chairman of a session will stop you 5 minutes ahead of the time, so that we can have some questions coming from the audience. All right, I still don't see Giovanni, and well then I think I start. So let me now change the role. I will stop being a chairman. Actually, I hope that Giovanni will join us so that he could be a chairman for my talk. But instead, I should serve myself. And let me start to give my talk. I think, it's probably going to be a bit shorter than the time I have for it. So let me start. Could you please confirm, anybody to confirm that you see my screen?
Yes. Screen. Mm-hmm.
Do you see my screen?
Yes, I do.
I think you cannot hear us.
I'm sorry, could anybody unmute and tell me if the screen is visible?
It is visible, but you cannot hear us.
Good, thank you. Yes, I cannot. Yes, Jose Manuel, I cannot hear you because you're muted. I can try to unmute it.
Can you hear me? Can you hear me? Jerzy, can
Let
you
me
hear me?
see.
It's George. Can you hear me?
Yes, you can hear us.
Oh, no, yeah.
Can you hear us
Okay.
now? Yeah.
No, I'm sorry. I was so overwhelmed by this prestigious role of being a chairman and a speaker at the same time that I forgot that I'm not using my speaker, but I use the headphone, so I couldn't hear you. But now you hear. Now I can hear you. You can hear me, I believe, and you can see my screen, right?
Yes. Yes.
Great. So let me start. What I would like to tell you is to describe briefly some work that we did recently with a large collaboration of people, and it concerned discrete symmetries and quantum gravity phenomenology. But I will spend most of the time describing some technicalities, and then I will actually have at the end I will make a kind of present a couple of general of slides which will tell you will provide you with a basic physical message that I wanted to convey. So the starting point is kappa-deformed field theory. We are working in a framework called kappa-deformed symmetries, and in this short talk I have no time really to explain what it is. It is based on a collaboration with these people. Do you see my cursor, perhaps?
Yes, but perhaps you would like to put the full screen, your PDF.
Oh, it's okay. Sorry. Okay.
Okay, perfect.
Yeah, that's
Thank
fine.
you.
Yeah.
Thank you. And this investigation is a starting point. This investigation I wanted to tell you about is a starting point of the research program that we're trying to work on step by step of constructing kappa-deformed standard model to understand really elementary particle physics, the formation of elementary particle physics from the point of view of deformed kappa symmetry. And of course, at the end of the day, we would like to confront the what we obtain. We would like to confront with observations. Okay, so let me start with the symmetries. I will not, as I said, I will not go. I will not really discuss any details of this theory. Well, for those who don't know, this theory is basically described in terms of the curved momentum space, which is kind of a half of say this upper half of the Sitter space. So the momentum space is curved, and it's closely tied to the space-time property, which is the non-commutativity of space-time. So you can think that you have a space-time which is non-commutative, and at the same time the momentum space is curved, and having this space-time and momentum space structure would like to construct the quantum field theory. What we wanted to do is to actually construct the quantum field theory in such a way that the C, P, and T symmetries are kind of manifest in the construction. This is kind of a major difference between this construction and the construction of the field theory, of numerous constructions of field theory that has been done in the past. And in order to do that, we actually need to double the momentum space. So instead of using, as it was customary before, just one half of the Sitter space, we actually use two halves of the Sitter space, one of them, roughly speaking, describing, so part of one describing the positive energy states of the particle, and part of another one describing the positive energy states of the antiparticle. When we and in what follows, and to understand the physical prediction of the theory, the one notion, which is a notion of theory of deformed symmetries, particularly the notion which is one of the basic notion of algebra theory, is the notion of antipode. The antipode means we need the antipode because we need to generalize something which you call minus. If I am in a flat momentum space, I know if I know the momentum, it's obvious what is the minus momentum. However, in the case of the curved momentum space and symmetries and non-commutative space-time geometry, it turns out that you need a generalized notion. And this generalized notion is defined to be as follows. The antipode of linear momentum of tree momentum is given by this expression, where T4 is just a constant. It depends on the deformation scale kappa and the mass of the particle. Omega p is just the standard on-shell energy. And you can easily see that when the kappa, which is the deformation scale, goes to infinity, this antipode becomes just the standard minus. So this is kind of a generalization of minus. And the basic property that we use, that we need this antipode to, is that if you want to generalize a plane wave, which is e to the IXP, then the dagger or adjoint of the plane wave is expressed not with minus here, but it is expressed, as it turns out, in terms or with the help of this antipode. So the antipode basically tells you, well, on the one hand, you can think that this is the generalized minus, but on the other hand, you may say that, well, this is the way to construct an adjoint of the plane wave. And having this equipped with this, we can construct the field. We can construct a field. This is a classical field, but expressed in terms of the Fourier coefficient A and B. Well, it should be really star in the classical language, but I just already used dagger, or you can think that this is a quantum field with A and B operators. And you see that, okay, the new ingredients here. First of all, there is a kind of additional measure factor, which is not that important and interesting. You can think of it as a kind of a measure that is just appropriate for the curved momentum space. You see that the plane wave here is just the standard plane wave. So we start with something which is a standard positive energy part of the field. However, you see that here already, when you take the antiparticle, you have this presence of this antipode which is present in the description. And then by using the antipode and the definition of the adjoint, you can actually find the field that's adjoint of the original one. And you see that again here is an antiparticle, but the antiparticle is not described with the plane wave is opposite sign, but as I said, it's really described in terms of the antipode. As I said before, we constructed the field in this way because then the action of discrete symmetries is just a standard one. It's naively speaking, it's just on the form, and you see that indeed the parity, time inversion, and charge conjugation act in a kind of a standard way. Then we can construct the action. We construct the action which basically the most general linear bilinear real object. Since the action, this is the space-time action, we integrate it over space-time, but because space-time is non-commutative, you can either integrate over non-commutative space-time, or instead you can use the commutative space-time, as we do here, but instead of the multiplication of the non-commutative coordinates, we use the special product, which is called the star product, which is highly nonlinear and non-local. So that renders this action non-linear. Well, it's still linear in field, but this is very, very non-local in space-time. Then you can also construct the momentum space action just by looking at Fourier transforms, and then you find something pretty interesting, because you find that the coefficient multiplying this term, which is the kind of a particle term, is p squared minus m squared, which is the standard mass relation. But for the antiparticle B, the the coefficient is S of P times squared minus M squared. It is actually, so that means that the moment that the equation, field equation for momentum for Fourier coefficients are just P squared equals M squared for the particles and S of P squared minus M squared for the antiparticles. Actually, the properties of antipode are such that as a manifold, the manifold P squared equal M squared and S of P squared equal M squared are identical. However, the points, as you will see in a moment, these points P, the point P and S of P on a mass shell are different from one another, of course. Having the action, having the kinetic term, you can actually construct the commutator for this modes, or Poisson bracket of this modes, and then you can quantize and find the creation annihilation operator commutator for the modes P and Q, which looks essentially like the standard one with some prefactor, which of course, if you like, you can actually absorb in the definition of these operators, but for some reasons that some other expressions are getting much more complicated, we actually choose to use these expressions. Then we define one particle state. So before I actually start this part, because this part is more physical, let me summarize what I have. I have a kind of a non-commutative geometry with associated to it curved momentum space. I construct some kind of a free field theory. I find from the Lagrangian from the action, I can find the creation annihilation operator algebra, just in a standard way. And now having this, I can construct the one particle states just in the standard way. So I define the one particle state with the label by the label P in this way, and one antiparticle state in exactly the same way. And the label is again the label P. Well, one thing that should be noticed here is that in the standard quantum field theory, the label of the one particle state is exactly the eigenvalue of the momentum operator. However, here it turns out to be not the case, and there is some kind of a deformation. So this label P for particle A and label P for particle B is not exactly, as you will see, or at least one of them is not going to be exactly the eigenvalue of momentum operator. And in order to check what it is, we need to compute the momentum operator. And it actually takes a pretty familiar poem with one little twist. So this is the Hamiltonian. It has this standard structure A cross A, but multiplied not by omega, but S of omega with the sign, with the minus sign. And here for antipower for the B sector, you just have the standard, the standard kind of it's not normal ordered, but if it was normal ordered, it would be just a standard number operator multiplied with this insertion of the energy. And similarly, the momentum operator has exactly the same structure, that it looks like, so the B sector, for the B sector, it is like in the standard theory, but in the A sector, the P is replaced by S of P with a minus sign. And then what we need also, what we find also necessary for the further construction, we can actually construct the boost operator, which takes this form, and the rotation operator, which takes this form. So in fact, what we construct from the for this theory, we constructed the full set of Poincare operators, and now we can ask ourselves, what is the algebra of these operators? It turns out that the algebra of these operators, you can compute them because you know the creation annihilation operator algebra, so you can compute the algebra of operators Hamiltonian operator, momentum operator, boost, and rotation. They satisfy the standard Poincare algebra. And this means that if I want to construct state boosted from a particular state by the finite boost, I can use just the standard Lorentz formula, right? Because the algebra here the algebra here is absolutely standard, which means that I can use the standard Lorentz expressions for the Lorentz algebra expression for the finite transformations. So what are the energy momentum of the state? Well, as expected, they are slightly different than the one that we had in the standard theory. So for what I call the antiparticle state, we have this expression, which are just the standard expressions. However, for particle state, we have expression which is kind of deformed. So we have the antipode instead of the minus antipode of omega instead of omega, and the same for linear momentum. As I said, this particle and that particle belong to the same mass shell, but in general, P and minus S of P are of course different. The only exception is that actually for in the case of the particle at rest, where P is equals linear momentum is equal 0, then omega of P is equal m, and if S of P is equal 0. If P is equal 0, then S of P is also equal 0. That means that S of omega is also equal m. That means that particle at rest is still characterized by the condition that for both particle and antiparticle, the energy eigenstate, the energy eigenvalue is actually m. Well, let us now think about C operator, and let me now turn to the most important message of this talk. As I said, C is a symmetry of the theory, and actually what the charge conjugation does in the theory, it actually does the standard thing. So it takes one, say, antiparticle state with momentum p and takes it into one particle state with momentum p. So the charge conjugation transforms one particle state labeled by P to one antiparticle state labeled by the same label. But the energies of momentum of some states are different then. That follows from what we discussed before, because the energy of the antiparticle state with linear momentum P is S of omega minus S of omega of omega P, and the energy of this state is just omega P. And the only exception is where the particle is an antiparticle at rest, because then the energy of particle and antiparticle is exactly the same and it's equal m. So that means that there is a funny and subtle deformation of CPT, C symmetry and CPT symmetry as well. If we boost the particle and antiparticle, which are initially at rest with the same boost parameter, we obtain a particle and antiparticle with the same momenta as measured by the momentum operator. Momentum operator is a device that measures for you what the momentum is. But these two moving particles will not be related to one another by charge conjugation, in spite of the fact that they were where the particle and antiparticle were at rest. So these states will not be related by the charge conjugation. And the reason why this happens is that the charge conjugation operator, you can construct an operator that actually acts as a charge conjugation and replace the A states by B states. Actually, this operator in the deformed theory, contrary to what happens in the undeformed standard theory, does not commute with the boost operator, except that when acting on a state labeled by zero momentum, so the state at rest. And this theoretical result can be actually used to do some little phenomenology and give some estimate on the deformation parameter, basically by having the muon anti-muon pair with very high energy, and then boosting it back to the rest state, and see. And well, since the energies of the C-related muon and anti-muon should be different by a small amount, also you can by analogy you may say that decay rates should be also different, because decay amplitudes are basically could be related to the imaginary part of energy. So you can assume that they actually Lorentz transform in the same way as the zero component of full momentum does. And then by doing some phenomenology and checking the data, we find from this pretty naive phenomenology, we find pretty strong lower bound of deformation parameter kappa, which is 10 to 14 GeV, which is some few orders of magnitude less the Planck mass, which is expected. Which is expected magnitude of the deformation if you think that this theory has something to do with quantum gravity. But one can hope that with in the future colliders with much higher energetic muons and the muon pairs, we can actually improve this bound by a couple for the magnitude. And also one can think about some more dedicated setup actually to measure this effect. And this is basically what I wanted to say. Thank you very much. And now I'm switching to the role of a chairman. And if you have any question, that's the question time.
So Jerzy, I do have a question, and I don't know if I asked you this question before. Hi, it's George.
Hi, Georgie.
What happens in the case of neutrinos? And what I have in mind is that people are searching for Majoranas, right? And in that case, in principle, particle is the antiparticle, right? And the lepton number is violated. What happens in that case if you cannot deform it this way that you are doing?
Well, all right. So there is one of the results that it's unpublished, but it's gonna be published in one of the papers in the series. The point is that if I understand correctly, you asked me about the real particle, right?
Yeah, I'm asking you about Majorana fermions. Let's say neutrinos as Majoranas, right?
Oh, well, so to make it simpler, I understand that the same question you would ask about pi zero, which is a real particle. So it's all antiparticle, right? So the theory of a real particle is slightly different. So you start from a kind of a different construction from the very start. So everything that so it's not the kind of a just a naive real part of what I did, but you can construct, and this somehow doesn't work. We have constructed a proposal for the theory of the real particles, like pions, and then of course for the gauge field, because photon is real, right? So we need this theory of the real particles, but we still really didn't work out it completely. So, but I'm aware of the. So basically, basically, as far as I can see it now, the theory of a real particle is not really the kind of a naive, taking a naive real part of what I have here.
Okay. Thanks.
Sorry, Jurek, I have a question. So the conclusion is that if I get it correctly, the theory is not relativistic, because there is one observer, the one who sees the particles at rest, that sees the same decay rates, but there are other observers that see the decay rates difference. Is that right?
This is something that that I am really thinking about. That's why I say that this discussion of the of the decay is kind of naive, and the reason is the following. Actually, in order to, if I understand the phenomenology of decay, what you do, you actually take a particle which is moving, and then you can boost it then you boost it to the rest state, because essentially the decay probability, decay amplitudes are measured for the particles at rest. So what you need to do is to take a neutrino, say muon, which is, I don't know, has TeV energy muon, you boost it to the, you take a Lorentz transformation, you boost it to the rest state, and then you know that what is the decay amplitude, and then you use, essentially the decay amplitude behaves like a time dilation factor, right? Because it multiplies time. So here we do it naively. We actually have a different Lorentz transformation for the particle and antiparticle, which means that in this sense, we assume actually that what this momentum operator, so this algebra, so what boost operator actually does, it acts as an active transformation, not the passive one. But this is something that I don't completely understand at this moment. If this boost, because the crucial point is that in this theory, the boost does not commute with charge conjugation. But the question is this boost a passive boost? So this corresponds to a physical change of observer, or is it an active boost, which corresponds really to changing particle at rest with a particle in motion? I tend to believe that this operator describes the active transformation, but I am not completely sure, and I think it's pretty, this is pretty subtle problem that we are working on right now.
Okay, thank you.
Okay, since I don't, I see that there are no other questions at this moment. Okay, so let me finish this question time. Now, let me see. Because I understand that then our next speaker is Eugenio Bianchi. Eugenio, are you with us?
Hi there.
Oh, hi. Hello. How, Eugenio? Look, it's 17:02, and because there might be some people trying to switch from one session to another, why don't we wait just 3 minutes before you start? But you can actually try to share your screen so we see that everything works fine.
Sounds good to me. Can you let me share? Probably we can now share one at a time.
Could you try to share, or is there any problem?
Yeah, it just tells me that I cannot share while other participants are sharing.
That's funny because no, I don't think. Okay. Oh, I'm sorry because I need to stop share. Okay, good.
I try. Can you see my screen?
Yes, I see your screen.
Can I? Yeah. Okay.
All right. Let me see. You have just 1 minute. Well, I think you can start. I mean, while I think that everybody who is interested is already with us. Please just start.
Okay, thank you very much. It's a pleasure to join you for this session. Yeah, I would like to tell you about something, well, relatively simple, something that I've been wondering and we have been working on together with Bekir Baitas and Pietro Donat. And it's the question of what happens to Poincare invariance once you have a minimal length or a lattice, but really in the simplest toy model. There are clear reasons why, even for a time model, this is interesting. That is, in a lattice field theory, we know that lattice provides a cutoff that results in a maximum momentum, and broken Poincare invariance on the lattice is to be recovered in some limit or in some phase of the theory. While on the other hand, in theories of quantum gravity with a discrete structure at the Planck scale, this discreteness is assumed to be fundamental, and so you want to reconstruct Minkowski and its own Poincare invariance as a property of specific states with long-range correlations. And we do have a question of what are really the conditions for recovering Poincare invariance, what selection of states and what selections of observables results into that. And it's well known that once you have a discrete theory, even a lattice theory, there are dangerous pitfalls, and plan is to rethink lattice observables and Brillouin fields in a way that might also be relevant for ideas in quantum deformations of Poincare symmetry and observer independent speed of light or maximum momentum. I also have to say that I gave a version of this talk at the DSR 20 celebrations. I got really helpful feedback and has made us think, and we have been thinking about some of the aspects that were asked. So we are going to see some overlap, but also hopefully some points that address those questions. I'm going to bring them up. Okay, so I have three parts. The example is rather simple and standard. I'm going to consider just a scalar field, a real massive scalar field in 1+1 dimensions. I'm going to do it somehow 3 times. First, review the standard classical or continuous version, then do the standard textbook discretization, first neighbor discretization and a variant, and then discuss the new proposal and the idea behind the new proposal. So let me first review something completely standard. That is, at the classical level, you can consider this Poincare invariant system. You can see the action here. And now I'm not going to work covariantly because I'm going to try to, I want to explore properties of systems that don't manifest Poincare invariance, but Poincare invariance can arise either in a phase or exact but not manifest. And so the pattern I'm going to take is to work canonically. So it's good to prepare things already here where we know everything and we understand everything. So canonically at the classical level, I have a phase space for my fields. And Poincare invariance is realized as a set of generators of time translations, space translations, and boosts that satisfy a Poincare algebra that is realized in phase space as these Poisson brackets. Now, we also know how to do this in the quantum theory. The steps are rather immediate. Poisson brackets to commutators. The Poincare generators, I have to quantize them. And the standard strategy is to introduce a modest function for the field that is such that these creation annihilation operators are not generic, but they are the ones that put the Hamiltonian in normal form. Once you do that, you find this frequency to be the familiar one. And then you can build a Fock space over this vacuum. It is by construction Poincare invariant. And these operators provide a representation of the Poincare algebra on Fock space. Okay, all this is standard. Now, what I'm going to do next is to discuss discretization of these 3 operators and the conditions of, and the fate of this algebra. What happens, what gets broken, what can be fixed in this toy model. So the first step is really the textbook version, like Muster and Monvey lattice field theory. So I'm going to consider a lattice, one-dimensional, equispaced, fixed-spaced L, and infinite. As discretization of the spatial derivative, I'm going to consider the standard first neighbor derivative, the backwards one, phi n minus 1. You can take the continuous Hamiltonian, substitute the derivative here, and substitute the integral with a sum, and you immediately get a discretization of the Hamiltonian. Now you want to build a Fock space, a lattice Fock space. So you follow the standard strategy. You look for a modest function that puts the Hamiltonian in normal form. Yeah, everything is time independent, so it's immediate. And what you get is the familiar fact that this omega L, which is nice to write in terms of this discrete derivative. This is going to play a role after. And this d minus of p is the Fourier transform, the discrete Fourier transform of the discrete derivative, modulo square, and here you get a term that is periodic in P, And every integral in P is bounded in this so-called Brillouin zone between minus pi over L and plus pi over L. And so this gives a full quantization of the system. You have a Fock space with a vacuum that is the vacuum of this Hamiltonian. Okay, so I have time translations, I have a representation. Now I can start asking questions about the system. And before Poincare invariance, I'm going to ask a simpler question that is the one of dispersion relations. Dispersion relations are properties of, in particular, one-particle states. You can ask, what's the energy of this one-particle state? What's the momentum? And what's the relation between the two? So I need a momentum. You have introduced only the energy. So one strategy that is somehow the one that you find in every lattice field theory book is that you do have a notion of lattice translation. It's the unitary operator on Fock space that shifts the lattice field from a site to the neighboring site. And then you can ask if this can be written as e to the I something Hermitian. I'm not going to call this PL the generator because, yeah, it's really for a finite step. So yeah, there's an L that I cannot send to 0. So if I try to write it in this form, that's the form of PL. So you see a P, the label of the Fourier transform. Now you can check the one-particle states that are what you obtain from the vacuum acting with this creation operator. Eigenstates of the energy to energy omega L, and of PL, this object that if I interpret it as really momentum, then this gives me a dispersion relation that I can, for instance, read at low momentum. There's a frame here, so in the lattice frame, and it's Lorentz violating at order L square, as we all know. On the other hand, a time momentum on lattice frame, that is when you get to P close to pi over L, there's non-trivial physics that we are familiar with from the physics of phonons in a crystal. That is, these things I'm calling one-particle states really behave as quasi-particles, and the physics of the Brillouin zone becomes important. So the remark is, well, what did you expect? You put a lattice, you broke everything. In particular, you didn't get Lorentz invariant dispersion relations without this additional term. Now, there is an interesting remark that came up at DSR that is, there's this fascinating work of the 90s of Bonecchi, Celeghini, Giacchetti, Sorace, Tarlini, who noticed that if you take that discretization of the Hamiltonian that I gave you before, the textbook one, and you take this unitary operator you have, and you add to them something else that you still have to build, that is something that you can think of as a generator of boosts. This one you have to build. Then these three together, you can think of them as what you need to build an algebra, but now it's not the standard Poincare algebra, is a quantum deformed one, EQ11, where Q depends on this lattice spacing. Okay. Now this is what happens if you use this UL, but here I'm considering a discretization, and I have the continuous versions of H, P, and K. So I could take a different route and just follow the standard path of discretizing everything, just naively. I have a continuous Hamiltonian, I discretize it. I have a continuous generator of spatial translations, I discretize it with this first derivative. And I have a generator of boosts, I also discretize it with this first derivative. Now, the first thing that you notice is when you discretize it this way, the generator of translations doesn't have a P here as before, but has this different quantity. And so you get a modified you get another set of dispersion relations, because that's this quantity is what you have to interpret as physically the momentum of the particle. But you can just take a different point of view of abandoning completely the question of dispersion relations and really ask this theory, this quantum theory, as a vacuum. Is it Poincare invariant in any sense, in any concrete sense? And so you can take these three and look at their algebra and see if, well, look at their commutator and see if they form an algebra. So the fact is that if I take these three and I compute the commutators, it's a bit tedious, but can be done, especially if you go to Fourier transform. You find that H with P, well, this one's commute, it's immediate to see. It turns out that K with H happens to give exactly this P tilde. So this is good. But the other one, those are close. On the other hand, if I had taken the discretization or the formulation described before, this one with this PL, that doesn't come from a discretization, but comes from by fiat, by saying this is translations. Then you find that these two close and reproduce what you have for the Poincare algebra, but the third one doesn't. So that raises a question that is the one that we explored. That is, can we take the continuous theory and put it on a lattice by introducing a discretization such that we really get a Poincare invariant algebra? Exactly, not with corrections. So here's the strategy. And this is the work with Bekir Baitas and Pietro Donat. We call this formulation a Brillion formulation on lattice. You're going to see where the name comes from. So the strategy is to take the discretization of the derivative as our parameter and see if we can impose the requirement of having an exact representation in Fock space of the Poincare algebra. So we need a notion of discretization of the derivative. These are the requirements that we put. We require that the derivative is linear. So you can think of it as a matrix applied to our lattice fields, infinite matrix perhaps. We assume that it's covariant under lattice translations. It just means that it depends only on n minus m. And well, that the derivative of a constant is 0. Now, once you have this prescription, it's immediate to write a discretization of what are the Poincare generators. You just put this derivative in K, P, and K, H, K, P, and K. Now, what we want to do, the plan, the strategy is to impose an exact Poincare algebra. It is impose this three relation. And the question is, first of all, does a solution exist? Is there a DNM that satisfies this property? And second, if it exists, are there many or is it unique? And my expectation was that that doesn't exist, that cannot exist. I never heard of that. We looked at that. The calculation is tedious. It turns out that the solution exists and it's unique. So what is the calculation? It's this is our unknown DNM. These are the definition of the three objects that would be Poincare generators, and you impose these three relations and you determine DNM. And the strategy is easy. You just go to Fourier transform and you solve for the Fourier transform of DNM. And I'm not going to show you the steps, tedious, long, but you know, straightforward. The unique solution is that this discrete derivative is a derivative that is infinitely many neighbors. So if one adds, is there a discretization of derivative with finitely many neighbors that gives Poincare invariance on a lattice? Well, the standard knowledge, the folklore theorem that it doesn't exist. Well, it doesn't. This is a proof that it doesn't. What exists and it's unique is a discretization of the derivative that is non-local with infinitely many neighbors weighted in this way. Now, you can ask what's the Fourier transform of this D of P, and it's just IP, just exactly as the Fourier transform of the derivative in the continuum. What is the difference? The difference is that the region of integration in P is the bound, the Brillion zone. And so essentially what is happening is that on a lattice, the physics of the Brillion zone, we know that is always present and relevant. And if you put on the lattice the objects that you have in the continuum restricted to the Brillion zone, you get, first of all, an exact representation of the Poincare algebra, a Brillion version of the Poincare algebra. And second, and that's what I'm going to discuss in a moment, you cannot really tell that there is a lattice with local measurements. So let me go to the next part. So by construction, you have introduced a Fock space and a vacuum, and the vacuum is Poincare invariant. It's annihilated by H, P, and K, so it's also invariant under all Poincare transformations. Then I can look at one particle states. They have definite energy and momentum respect to PB and HB. And the energy and momentum, you read it from the dispersion relations, and the dispersion relations are not the lattice ones, the ones with the deformation you see here, but they are the ones that match exactly the continuous ones as long as you are in the Brillouin zone. And then when you are outside, well, they behave as quasi-particles. That is, in the Fock space, a particle with momentum P plus 2 pi integer over L is the same state as the one with momentum P. And the picture is the standard one of the physics of the Brillouin zone. That is, if you can measure things only at lattice sides, you cannot distinguish these two frequencies, the low one and the high one. The thing that I find more surprising, that to me was really testing that the idea works, was, is it true that if I take a one particle state and I boost it, I find the boosted one particle state? And it turns out that it actually really works together with the identification at the bounds of the Brillouin zone. It is non-trivial, I would say. And as a consequence, the fact that at least if you look only at these one particle states, you cannot see the lattice. Now, there's a separate question of, are there also field operators like the ones that I introduced from the very beginning, this one, that I can study and study the transformation properties. And again, it turns out that the field operator transforms under translations generated by PB and boosts generated by KB in a way that it is non-local, but if evaluated at the lattice sites, it's actually local and covariant. Okay, so let me go to some comments before closing. I said that this discretization of the derivative is non-local. It has this fall-off properties. However, there's a separate question of a class of observables that one can focus on. For instance, instead of looking at the field at lattice sites, one can look at a smearing of the fields. A smearing with some smearing function that is supported in a region that is large compared to the lattice spacing, but still small compared to other scales. For instance, I can compute like commutators of fields or correlation functions of fields located here and there with nice peakiness properties. So once I compute these probes, the remark is the following. So this is the lattice field, and this is the probe of the smearing function that is somewhere compactly supported. If you write it in Fourier transform, this Fourier transform is a band-limited function by construction, and it turns out that a lot of the intuition in the physics is the one of band-limited smearing functions in the continuum that Kim Kempf and others have proposed. And here you have a concrete realization of that notion of band-limited fields or band-limited observables, with on top the notion of Brillouin periodicity that is not in these works. The second remark is that there's older work within the lattice community that goes under the name of perfect actions and also order by order improved actions, starting with the work of Szymanczyk. That is, can we write a lattice theory that is indistinguishable from the continuum theory by just taking the continuum theory and renormalizing it to the lattice? And you end up with coupling or interactions terms of this kind with this kernel. And it turns out that in the example that I worked out, they determine exactly, well, this Hamiltonian if they were to do it canonically. They generally do it covariantly with a discretization of time too. Okay, So another question that I want to address briefly is the idea of how a causal structure can arise in these brilliant lattice theories. And if one can reconstruct the causal structure by looking at commutators of fields. Because in continuous field theory, there are properties that we expect to be exact because you start with the causal structure and on a certain space-time, and then you introduce fields. But here, there's no space-time and there's no causal structure. So one can try to reverse the logic and look at the commutator of fields at different space-time points and see if it vanishes at what one would infer as space-like separation. So here you see the continuum. For a massless field, it vanishes outside the light cone and it doesn't vanish inside the light cone. This is the standard textbook discretization. It has this funny structure. It doesn't vanish outside the light cone with the first neighboring discretization of the derivative. And here is with our discretization. And you see that still, it doesn't mean that it vanishes. It vanishes at lattice points at equal times. And then it has a specific behavior at specific times as a function of time. But this is for the lattice fields without any smearing. So now I can introduce a smearing that is of this kind. So clearly in these pictures, there are two scales. One is the lattice spacing, and second is, this is a commutator of two fields at 2 points. One is the origin here. The other is where I'm putting the probe. And so I can look at observables that have a smearing that is large compared to the lattice sides, and it's small compared to the separation of the 2 points in the correlation function. And once you do that, you find that you recover a light cone structure with exponentially small correlations outside what you could infer as the light cone. The second remark is that if you were to do in the continuous theory a smearing with the same smearing function of probe, you would find exactly the same correlators and the same commutators. So in this sense, on this subalgebra of observables, the one we're calling the Brillouin subalgebra, the continuum theory and the lattice theory are completely indistinguishable. Okay, so to conclude and summarize, I discussed a toy model of a lattice theory where the lattice is non-observable. The features that it has, it's a discretization, it is non-local. The benefit is that we get an exact representation of the Poincare algebra in Fock space. And there's a subalgebra of observables that clearly has a maximum momentum periodicity. From the point of view of what we learn for theories of quantum gravity with a fundamental length scale, I think that one thing one learns is that the reconstruction of Minkowski space as a state or a specific regime of the full theory may require both a state with long-range correlations and the restriction to a subalgebra of observables that is insensitive to the microscopic structure. And here in this toy model, one has a specific example where the long-range correlations come from the Hamiltonian. But the Poincare invariance really comes from restricting to a subalgebra of observables. And the second message from the point of view of phenomenology is that one could expect that a minimal scale just gives modified dispersion relations. And this is somehow a counterexample. There are no modified dispersion relations. You cannot tell that there is a lattice by looking just at one particle. On the other hand, if you look at the scattering of particles, one could find something that is well known in crystals, that phonons scatter. And when they scatter, if two phonons of high momentum close to the boundary of the Brillouin zone, they have conservation of momentum that is not sum of the two giving the third, but sum of the two giving the third modulus the Brillouin band that is known as backward scattering or unclapped scattering. And if we were to see something of that kind, that would be a different kind of consequence of minimal length. Okay, I'll close here. Thank you very much for the attention.
Thank you, Eugenio, very much for your nice talk. Could you, if anybody wants to ask question, because we have some 10 minutes for question time, if anybody wants to ask question, please raise hand.
Hi, Georgie.
Hi, Eugenio. Can I ask a question, Jerzy, or no?
Yeah, sure.
All right. Nice talk, Eugenio. Good to see you again.
Good to see you too.
So I completely agree with your conclusions that if you have a minimal length, you don't really have to destroy Lorenzo Poincaré, and that there is sort of some sensitivity, that there is essentially some essential non-locality then coming in the description of the physics. So I've been thinking about some of these things you probably know with Laurent and Rob, and also with Jerzy in a different context, in which the dual lattice also appears. So this is what I wanted to ask you. For example, one of these sampling functions that you mentioned, you see there's something what they call the Zac transform, which is essentially the following. You take a lattice, and then you take the dual lattice, like so Fourier transform one, and so you discretize your fields on the lattice, but you Fourier transform with respect to this dual variable. It's like having with your operator U, you also have this V operator associated with the translations on the dual lattice, and they're like clock and shift, you probably know. And so does this ever appear in your construction? Like, for example, if you took this, if you constructed, let's say, a state which is, let's say, a Gaussian, okay, a wave packet, right? Then if you did this a Zac transform, this particular sampling, which is optimal sampling, then you would get a theta function, because you know, you would satisfy exactly the periodicity conditions on the lattice on the Brillouin zone. Did you encounter anything like this, the role of the dual lattice in your analysis?
Yeah, it's an excellent question. We have been looking at it, in fact, after we discussed quite some time ago. There is, in a sense, a dual lattice in the standard sense of you know, having the Brillouin zones with periodicity. There is a special class also here of smithing functions that correspond to the Zac transform. However, I cannot tell yet if you have exactly the kind of modularity that you would like to see, both on the lattice and on the dual lattice. Okay. Somehow here the construction is you want to have exactly the same theory as the continuum one, and you get as much as you can get. So in that sense, we are not imposing the duality, we're imposing something that is strongly attached to the direct lattice.
Okay, so you don't have modularity at the moment, right?
No.
Okay.
No.
So another question is...
Sorry, Georgie.
Okay.
I'm sorry, but we have pretty short question time, so
okay.
so we need to give a chance to some other people. Dr. Novak wanted to ask question.
Yeah, hi. Please, did you compare your results with the results in loop quantum gravity? I mean, because you start with continuum, you also obtain discrete structure, and you have some minimal length. So where lies your framework is completely general, if I'm right? Okay.
Yeah, thanks for the question. My motivation was trying to learn from a simple toy model how Poincare invariants might arise in theories like quantum gravity, where there's certainly an additional difficulty, that is the theory doesn't have Poincare invariants in the same way as general relativity doesn't have it. No, it's in general relativity is a property of one classical solution, Minkowski space, and you cannot impose it as an exact symmetry on the full Hilbert space. It's over constraint. However, you can ask if in the Hilbert space of the theory there are states that have some approximation of Poincare invariance as a property or some notion of asymptotic Poincare invariance. So the thing that we have been looking at is sectors of the Hilbert space of the theory where, for instance, correlation functions are long length enough to be insensitive to the fundamental scale, and all these are properties of states themselves. And I think that what I'm learning from this toy model is that you need to do more than just restrict to a corner of the Hilbert space and look at some states with specific properties. You have to also restrict to a class of observables. So in this sense, I think that is the lesson for what one sees there. But on the other hand, if you're thinking of like loop quantum gravity as a discretization of general relativity, it's a top-down discretization. So we're not introducing a notion of lattice derivative. So I don't have a direct analog to this construction.
Thank you.
Before since I don't see any other hand, may I ask my question? And if we have time, perhaps we can let Georgie ask his second question. My question is pretty, if I understand, pretty short. If I understand correctly, you have a two-dimensional system, right? Only.
Yes.
Do you have any idea how it's gonna work when you extend to 4 dimensions, say? So when you include rotations?
Yeah, good. Yes. So these are things that we have looked at. So I can tell you that massive scalar field in 3+1 with a cubic lattice, everything works exactly the same. So there's not much to add in that case. Then the more complicated question arises when you do like a fermionic field. So fermionic field, the question arises already in 1+1. On the lattice, it's known that there is this fermion doubling. So it turns out that here there's no fermion doubling. It evades the standard no-go theorems because of no locality. And then the third thing that goes into the same direction of generalizations is I could introduce an interaction. That's something that Ted Jacobson was asking last time in this talk. And so we checked if you could introduce a 5-4 interaction and you work with it perturbatively, you still preserve Poincare invariance, which is somewhat non-trivial. So this thing that I was discussing, well, I had to do it perturbatively, but it generalizes also to interactions. Interactions have to be still compatible with this physics of the Brighian zone. And then the last thing that we haven't worked out yet, but I think we would learn something from that, working out that example, is doing electromagnetism on a lattice. And the reason is that, as a preparation for Ian Mills, and the reason is that people who do QCD simulations put on the lattice Ian Mills, making sure that gauge invariance is exact on the lattice at the expense of Poincare invariance. And so, yeah, we are requiring exact Poincare invariance. And the question is, can we require exact Poincare invariance and exact gauge invariance on the lattice? And I don't know the answer, but it's something well defined that at least for U1 can be answered completely by just working it out, at least in 2+1 or maybe in 3+1. And what I expect is that this discretization of the field strength is not going to be with a Wilson loop of single plaquette, but with a superposition of Wilson loops of plaquettes that are large, not plaquettes, but loops that are larger and larger, of a kind that we did study in the loop representation of loop quantum gravity, or how this superposition of loops arise. So that is a 3+1 case that I consider a non-trivial test of this idea.
So to put it short, in the case of a scalar field, you're saying that you can generalize everything up to 4 dimension 3+1, and the algebra becomes just a standard Poincare, right?
Exactly.
Okay, good, thank you. I'm afraid we actually reached the end of this time for Eugenio. Thank you very much.
Thank you
for your nice talk and discussion. And next speaker is Monica Ramirez. Are you with us? I mean, I see you, but could you switch on your microphone and camera, please, and try to share your screen? Hello?
Yes, hello. Can you hear me?
Yes, I can see you. Okay, I can see your screen too.
Okay.
Okay, you can start. You have 15 minutes plus 5-minute question time.
Okay, thank you. Thank you everybody for coming to my talk. So this work on spin forms, gamma duality, and parity evaluation in primordial gravitational waves is a project I've been working on at Penn State with my supervisor, Eugenio Bianchi, who was just talking to us. So we want to solve this question, which is, can we make any phenomenological predictions from an effective action for inflation which respects the exact symmetry called gamma duality of spin forms? I will try to make this clear to you in 3 parts. So first I will explain to you what is spin forms, or not spin forms, but what is gamma duality on the context of spin forms. How will we use this to construct an effective action for inflation? And what does this imply for tensor modes? Okay, so first, for context, loop quantum gravity and spin forms are a proposal for quantum gravity theory. And LQG is or loop quantum gravity is the canonical approach, spin forms is the covariant approach. In this theory, quantization of gravity means quantization of space-time. And what is this gamma that I have? The gamma that I have on the title of my talk? Well, this is known as the Barbero immersive parameter. And what is the role on the quantum gravity theory? It plays a role both on dynamics and also on physical observables. It appears on the spectra for geometrical observables. So I put here just one example for the area of the surface on a chunk of space after quantization. The theory has 2 fundamental constants. One is the Planck length, and the other is the parameter gamma. Okay. So what is gamma duality? At the core of quantization for both LQG and spin forms, we have the classical Holst action. So in the tetrad language, we can write the equivalent to Einstein-Hilbert action, which is known as the Einstein-Cartan action. This one is where this is the curvature, okay, and these are the tetrad. So the Holst action, Einstein-Cartan Holst or just Holst action, consists of that term plus an additional term, which vanishes on shell. So this has no contributions to the classical equations. However, after quantization, the loop program of quantization, it plays a fundamental role, as we mentioned before. It will appear on the spectra of observables. So translating to metric language, this, as I said before, this is the Einstein-Hilbert action. This term becomes this expression. They have been studied. We know that this is an even parity term, while this is odd under parity. Okay, and then to tell you what is gamma duality, let me refresh the dual decomposition into subdual and anti-subdual parts. So this star that appears here is the Hodge dual, which is an operator acting in 2 forms. This is the Levi-Civita tensor acting on internal space with this totally antisymmetric and with this convention. Okay, so you can define projectors using that operator. They are projectors because they, by themselves, give itself. So you have two of them, plus and minus. notice that the sum of both gives you identity, and also that Hodge dual times the projector gives you plus minus number times the operator, which means that you are projecting into self-dual and anti-self-dual parts. So this allows us to split any two form into the self-dual and anti-self-dual parts of it. So here I wrote the indices, but I may drop them sometimes, as I did here. Okay, so now let me define an operation. So we want to know, is there any way of understanding how to go from an even parity action to a mix of even and odd parities? Okay. So for that, we define what is let's call here in this talk a dual rotation. So it is a one parameter family of transformations in which you take the self-dual part of the curvature and rotate it in this way, while the anti-self-dual part you rotate the opposite way. If you did the same way, well, you get just an overall factor, so it has no meaning. That's why we call this dual rotation, because both parts transform opposite. Okay. So what happens if we apply this transformation, for example, to this term? You get this expression, and you can easily recognize this term is what we had before. This term is the odd parity term that we wanted. So theta is the angle theta is determining how much of odd or even parity terms you have in this transformation. Okay, and of course this only tells us relative factors. So because the overall factor has to be determined with physics, so you can absorb the coefficient that was here, which was a cosine theta. It cannot be distinguished from here from an experiment. So this tangent theta will be the relative factor between the two of them. And this way, then we can define what is gamma duality or what is a gamma dual action. So a gamma dual action is one whose components, even parity and odd parity components, are related to each other through a dual rotation with this special angle. So such that tangent theta is equal to 1 over gamma. Okay. I should point out that people have also phrased the gamma duality in this form. And it is, if you take the self-dual and anti-self-dual parts and you switch them in the action, and also change the sign in front of gamma or change the sign of gamma, you get back the same action. So this discrete symmetry gamma duality is phrased this way sometimes also. Okay, so that was part 2. So I just told you about this exact symmetry of spin forms. Now we want to connect to phenomenology. So there's nice works that have been done before. People have found multiple ways of connecting the theory to phenomenology. Some of them have made use of this symmetry in spin forms and try to apply it to their models. But yeah, you can see them. This is for reference. Of course, there is more that I'm missing here. So let me remind you, how are we going to do this? So what we want is to connect quantum gravity theory to phenomenology of inflation by making use of this exact symmetry gamma duality and effective field theory methods. Okay. So how are we going to do it? So then let's construct the effective action for inflation. At 0 order, we have the Holst action plus an action for a scalar field. We're going to take the simplest model for inflation, a scalar field. We just demand that it has a slow roll phase. For constructing the next correction to this, we are just going to use the same elements that we had on the Holst action plus the inflaton field, scalar field. Okay. We demand that this action is gamma dual, the same way that we had at this order. And the lowest order correction turns out to be one that is made up of 4 space-time derivatives. This is an important point, but I'm not going to go over it. You can check it here on this paper by Weinberg, in which it can be seen that lowest order correction means 4 space-time derivatives after this. Okay, and our case study in particular, as I said, slow roll inflation. We will set torsion equal to 0 because it is not necessary to see the principle that I am illustrating. And we will focus on tensor perturbations. So after those considerations, the relevant term is the gamma dual, or the dual rotated version of this term, which is this. Okay. And yeah, so then from here, we can see this term is even parity. This one is odd parity. And maybe if I write it in metric form, it could be useful. So these are known terms. So this one over here is known as the Gauss-Bonnet term. And this one over here is the Pont-Regin term. So I should point out that without this coupling to the scalar field, to the inflaton, these are just topological terms, and they are not gonna tell us anything new. They have no effects on the equations of motion. So this one is important. It should not be a constant. And notice how the immersive parameter appears in this way. Okay, this is an odd function of the immersive parameter. Okay, and then we will start going into the cosmology. So our metric consists of Freeman, Lemaitre, Robertson, Walker plus a perturbation, tensor perturbation. We choose the basis for the tensor perturbations to be circular polarization, so right-handed, left-handed. And that way, this one over here is the effective action for the tensor modes. Okay, so it looks a little ugly, but main points. So you can see there is gamma everywhere, but in particular, it appears next to a term, next to a sign, because the right-handed and left-handed modes will have different actions, which means different evolution. And this is next to gamma directly. Notice also that, again, if I didn't have F dot or F double dot, then this and this is just the standard action for tensor modes in general relativity. The equations of motion at this point are a little ugly for me to show them here, but there is something else we can do that we haven't done, which is slow roll approximation. So there's different ways of dealing with this, but in particular, there is this good reference. So for consistency, one will need to—
Excuse me, you have 1
Yes.
minute, so please turn to your conclusions.
Okay, thank you. Okay, so one needs to introduce an additional slow roll parameter, which is the sigma, basically telling us that this function also varies slowly. And after treatment of the perturbations, then we have, as a result, that tensor tilt is different for right-handed and left-handed modes. And this dependence, this parity violation, is controlled directly by the immersive parameter. Similarly, the polarization is given by this expression. This take it illustratively. So this is different values of the immersive parameter. So you see different ways in which polarization would appear for close to some reference mode K star. Okay. So these are our conclusions. an effective action for inflation that respects this exact symmetry gamma duality of spin forms and QG exceeds gravitational parity violation. And this immersive parameter controls how much polarization we have and the tilt, how the corrections to the tilt on the tensor modes, which someday could tell us something about the quantum gravitational theory from experiment. That's it. Thank you very much.
Thank you very much for a nice talk. Questions, please raise your hands.
So I have a brief question for Monica. Very nice talk, very nice topic, very nice physics. Did you actually have some numbers? I mean, some estimate of how big this could be? And
nice question. Yeah, so we cannot really tell numbers because there is a caveat, no? That this sigma over here depends on the coupling, which we have not specified. So we will need some other observable that will give us a bound on this other parameter, but that's future work, yeah. Mm-hmm.
Okay, thank you.
Thank you.
Some more questions? Okay, thank you. Thank you very much for your talk. We have still 4 minutes. So let us, again, let us take a little break because there might be some people just wanting to join us for the next talk. Dr. Said Razgou, hello.
Hi,
I see you. So why don't you try to share your screen so that we are ready to start, but let's wait just 3 minutes.
Sure. Can you see that?
Yes.
Perfect.
So we have just, let me see. Yeah, we have 3 minutes break. So please wait. Okay, it's 6 o'clock now, so we can start. Please go ahead. And if I remember correctly, yes, you have 25 minutes plus 5 minutes question time.
Okay, thank you very much for the organizers to give me this opportunity. So this talk is about a series of projects that we are currently carrying forward. So this is about the polymerization or some sort of non-perturbative quantization of gravitational waves, and studying some of the possible observational consequences. So let's start by the classical setting of this work. The classical setting is, as usual, there is this Einstein gravity, Einstein Hilbert action. We can also add to it the cosmological constant. So what we do, as always, turn the background or decompose it into a background, the whole metric into a background and perturbations. So G0 here is a background. We take it to be the FLRW background metric. The advantage of that is that you have the possibility of studying gravitational waves that are coming very far from us, cosmological ones. And also, if you just put this equal to 1, if you want, you can study, or something constant, you can study closer objects which are not really affected. The gravitational waves are not really affected by the expansion of the universe. A is the scale factor, as is clear, and we have the perturbations, and we study them in synchronous transverse traceless gauge. Again, this is very common in gravitational wave physics. So having all that in mind, again, we go forward and decompose the perturbations into cross and plus polarizations. And now cross and plus polarizations, this sigma here is the polarization. We can write them in terms of these curly A's. Now these curly A's, so this Fourier decomposition, are canonical variables. So K is the wave vector, sigma are the polarizations, and these A, sigma, K are a configuration of variables for canonical theory. The momenta conjugate to them are these curly E's, which are just simply called E. And using these two basically canonical variables, we can compute the algebra of the model. So it simply turns out to be deltas. Now just note that we are quantizing the H's on a torus T3, and the length of that torus is L. So basically what you see here is the sum instead of integral over K's, but really it doesn't really matter. You can just go on and do it with an integral, and in principle, well, there are some mathematical issues may arise, but physically they're the same equivalent. Okay, so after doing all of that, you replace that in the action, Lagrangian, do the Legendre transformation, and then we get this Hamiltonian. So if you look at this Hamiltonian, there are a few points to note. Again, these sigma, K, and A, as I mentioned before. However, if you see the Hamiltonian, this Hamiltonian looks like, just apart from the sums, looks like a set of decoupled harmonic oscillators. This makes life much easier to quantize, to do whatever we want, so they're not coupled oscillators. However, as we will see later, there is one important obstacle, that this harmonic oscillator here, the Hamiltonian, we have this term omega squared here. This is the frequency of the oscillator, and this is time dependent, and because of the presence of the scale factor here. So in order to make things a little bit simpler, what we do is that we choose a certain gauge in which the lapse is just a cube. This is called the harmonic gauge, and we call the time corresponding to this harmonic gauge tau. And then we can write the whole thing as what you see here, with just this term goes away. And H here, which is the Hamiltonian that we are going to work with, turns out to simply be this term, which is basically the harmonic oscillator, but with omega squared, a time-dependent omega squared here. So this is a time-dependent harmonic oscillator that we would like to polymer quantize. But as we will see later, the polymer quantization of time-dependent harmonic oscillator is not well understood or well known. So we use a novel approach to polymer quantize that. But before that, I'm mentioning polymer quantization, all of these. Let's just see what polymer quantization quickly is. So polymer quantization is very close to loop quantum gravity. Let me just explain very quickly loop quantum gravity, the main differences with usual Schrödinger representation. So in loop quantum gravity, operator corresponding to the connection. So loop quantum gravity is a theory based on connections. You have the Ashley-Kerr connection, its conjugate momenta, which are densitized triads. Now, if you go to the quantum theory, in the Hilbert space of loop quantum gravity, the connection operator does not exist. This means that this is an infinitesimal generator that basically generates transformations in triads. So because this does not exist, you don't have infinitesimal transformation in triads, you have just finite transformation, and that consequently leads to just having finite diffeomorphism in Hilbert's space of loop quantum gravity, not infinitesimal diffeomorphism. And then you can, from that, basically you can interpret that as quantization of a space. So in any case, you don't have this. However, what you have is the operator of the holonomy of the connection. The holonomy basically is the parallel propagator of SU2 objects in this case. So if you want to move around the SU2 objects, you use this, you act the holonomy on them, and you get that. So this, now you can think of that as an exponentiation version of A, and that means that you have only finite transformation, because that's like a group member. This is like the algebra member. Okay, so because of all of these properties, the Hilbert space of loop quantum gravity is unitarily inequivalent to the usual Schrödinger representation. That basically means that Hilbert space is totally different, and you have different physics. Once you want to do the quantization and get an effective theory or effective Hamiltonian, you can do that as usual. So write the quantum Hamiltonian and then act it on some suitable states, and then get your effective Hamiltonian. Or in many cases, especially with finite degrees of freedom, you can just do this replacement directly from classical Hamiltonian and go to effective Hamiltonian. So for example, you have connection, you replace it with sine of delta A over delta, where delta is some minimum scale in the theory. Very well. So in the same way, we have polymer quantization. As I mentioned, this is something that mimics loop quantum gravity. Actually, it's independent of loop quantum gravity, but it mimics closely loop quantum gravity in finite DOF systems, degrees of freedom. In this case, some of the canonical variables operators do not exist on the Hilbert space. So for example, some of Q's or P's do not exist, the operators. Again, if these are infinitesimal generators of infinitesimal transformations. So if they don't exist on Hilbert space, you don't have infinitesimal change in the conjugate to these variables. Instead, some sort of holonomy or exponentiated version of these exists on the Hilbert space that gives you finite transformations of the conjugate variables corresponding to Qj, for example. And this mu here, as you see, is the same as delta in the previous case. There are some minimum scales in the theory. And in order to go to the effective theory as before, you can again go on and quantize the theory, quantize the Hamiltonian constraint and act it on some suitable states. And then get your effective Hamiltonian, or just directly do this replacement. Q or P goes to sine of mu Q divided by Q with minimum minimum scale. Okay, very well. So we are going to polymer quantize this. Again, the Hilbert space is quite different from the usual Schrödinger representation. Now, remember that this was my previous slide. I mentioned that I have this Hamiltonian, time-dependent Hamiltonian, and I want to polymer quantize it, but it's not clear how to polymer quantize a time-dependent oscillator. Now, in that case, what we do, we did a novel new approach to this, and this is the approach. So schematically, I will explain this in detail here, but schematically, what you have, you start from here. This is the usual phase space. You have Q's and P's and a Hamiltonian, which in this case is the time-dependent harmonic oscillator. And in the first step to overcome this problem, you go to the extended phase space. This is this case. So you transform your system to extended phase space. How is it done? You take your action. So this is your action, basically the PQ dot here. This is Hamiltonian. And your Hamiltonian is the time-dependent harmonic oscillator. What you do is that now you introduce your time and the momentum conjugate to this time as new canonical and canonical pair, and you write your new action in terms of a new parameter tau, and then PT and T are entered into their phase space, or you extend your phase space. But to ensure that these two basically correspond to each other on shell, you have to impose this phi constraint. Lambda is a Lagrange multiplier. Which means basically that P is equal to your Hamiltonian. So this enforces on shell, these two actions would be the same. The next step is, now that you are here in the extended phase space, you see what I'm doing is basically time independentizing, something like that, making it time independent, my system. So now I'm here. So the next step is completely make the system time independent. I make a special canonical transformation, and this canonical transformation is the heart of this method, and this goes like that. So suppose that you have your Q and your P, a small Q and P, and PT and T as your extended phase space canonical variables. You do this canonical transformation to capital Q's, capital T, P, and PT, and there is an auxiliary parameter here, rho, but the rest of them you know about that in the harmonic oscillator. So this makes my system, if I write it now, you will see in the bottom line, actually, this is the Hamiltonian at the end I get. This is time-independent harmonic oscillator. So after doing this canonical transformation, where rho should satisfy this relation, and you see it depends on the frequency and on the time-dependent frequency, and on something called W here, as you see here, and W plays the role of time-independent frequency of the new Hamiltonian, that canonically transformed Hamiltonian. So from here, you see that the action turns out to be, in terms of these capital variables, canonically transformed variables, and your phi, now it becomes phi tilde, the on shell constraint, the constraint that should be enforced on shell, and you can read your Hamiltonian here now, the time-independent Hamiltonian. And basically, this is in new variables, it is a harmonic oscillator that is the usual term harmonic oscillator. Okay, so everything is now set. As I mentioned, this is the time-independent frequency. Now, this rho has an important role. Actually, rho depends on, in our case, remember that, so here you see that rho depends on this W, which is a basically constant in time. but the time dependence comes from omega, time dependence of rho. And this omega related is, in our case, is related to the background, the space-time, to the scale factor. So rho is basically dependent of the background. So if rho is constant, you're basically dealing with a universe or something that doesn't have any scale factor. It's not expanding or contracting in that sense. And if rho is time dependent, you're in the realm of FLRW or other models with A. And what happens is that the form of this rho that defines omega, the form of this omega that defines rho, and also this capital W, this depends on the background, the scale factor, and the form of the dependence of A on T. Okay, so now we are here. We have a time-independent system. Now everybody knows how to polymer quantize. I mean, everybody in the field of polymer quantization knows how to polymer quantize the time-independent harmonic oscillator. So then we get an effective Hamiltonian here, time-independent effective Hamiltonian. Polymer quantized. The next step, which is step 4, is just return back the system to, as you see here, to the state that it was before the canonical transformation. So return everything back from capital Q, capital P, capital T, and capital PT to small ones. And finally, we get back to the usual Hilbert space, not the extended Hilbert space, and that gives us back the time dependence of these Qs and Ps. So at the end, we get a polymer effective time dependent Hamiltonian. And that is the result of what we get here. Just a word of caution here, or note, that polymer quantization basically comes in two versions, if you want. One of them is when you polymer quantize E, and it's always when you polymer quantize some variable, its conjugate variable becomes discrete. And what I mean by polymer quantize or polymerization of something, it means that basically you remember the exponentiation that in a very simple language. So basically I'm exponentiating E, and because of that, E takes values, compact values, and then conjugate variable A will be discrete. So this is the case of interest for us. There's another case where you polymerize A and E becomes discrete, but A becomes, remember that A was related to our perturbations, so we want our perturbations to be quantized. So this is the case of interest for us. And the Hamiltonian becomes this monstrous thing that you see here. It depends on rho and its time derivatives, and the mu and everything. So mu here is the polymer parameter, which sets the minimum scale of the theory. And the rest of the variables you know about here. The canonical or the equations of motion are now here. You can see them. And these, if you put mu, take the limit of mu going to 0, they turn out to be the classical equations of motion. I mean, classical, I mean non-polymerized equations of motion. Okay. So just quickly note that in the other type of polymer quantization where A is polymerized and E is discrete, this is our Hamiltonian. These are our equations of motion. It's much simpler, but we are not really interested in that because we want the gravitational waves to be discrete. Okay, so from now on, I'm just considering this case, the discrete A or discrete gravitational wave case. Okay, so let's consider first the time-independent background, time-independent case. And in that case, my A becomes this, the solution to A. This is an analytical perturbative solution. I will show you also the non-perturbative solution. You see that, first of all, there's a phase shift here. So this usual omega KT here or omega here. And then you have this phase shift here corresponding to mu squared. And you have an excited harmonic here. And of course, we have higher orders harmonic, but this is the first order. I mean, the first approximation. So the frequency shift is actually more important observationally. The reason is that this is depending on, and this term is multiplied by t, and that this t is the time that the waves travel. And for large distances, and any object that is far from us, large enough, that accumulates over time, and it becomes very important. Now, this is the full non-perturbative solution. What you can see here, just look at the green lines here and the blue lines. The red line and the other line, so they're not important. The red line is basically the other polymer quantization I mentioned, which we are not interested in. So you see, for small values of mu and nu, it's not very clear. The difference is not very clear, but if we put the mu larger in some certain units, you see that the differences. So basically, the green one is the propagation of the gravitational waves, classical gravitational waves. The blue one is when this A is discrete, the perturbations are discrete, quantized. And you see that basically what we have is a frequency shift and also the time of arrival shift. So the form of the wave and the time of arrival will change. And to see the difference in the time of arrival, we just find the group velocity of these objects. So you can actually read it also from the phase shift here, the shift in omega. And you see that the velocity becomes this. This is again perturbative, but I mean, this term, this graph is not perturbative, but this term is perturbative. And you see that the difference in the speed of the group velocity of the polymerized waves, first of all, the velocity is smaller than the speed of light with this negative that you see here. And the factor is k squared epsilon I mu over 4. Epsilon I is the initial value of epsilon or momentum of the wave. Mu is the polymer scale, minimum scale of the theory, and k are the wave vectors. So you see that this depends on these three, especially in this form of polymer quantization. The dependence on k signals Lorentz invariance violation, and also means that higher energy waves propagate at lower speeds. It means that maybe one can interpret that as higher energy objects, waves see the quantum regime or quantum structure of space-time, like they can probe it deeper, so they're more affected by that. It's just an interpretation. Okay, so this is the case with time-independent case. I just quickly note that if you wanted to go with the other polymerization scheme with not discrete H but discrete E, this K would not appear here. So you wouldn't have Lorentz invariance violation in the other case. But again, this is the case that we are interested in. In the time-dependent case, what happens is that you see things are a little bit different. First of all, you have a change in the also in the amplitude of the wave. But this, most of it is actually not related to the polymer quantization. It's just because the time dependence of the background. So it happens also without the polymer quantization. But again, you see some sort of phase shift or frequency shift, if you want, basically. And this frequency shift, again, is related to mu squared and k. But it depends not clearly how, I mean, it's not obvious how it depends on t itself. I will explain that later. But again, you have a higher harmonic, excited harmonic here. And again, frequency shift is very important because when times go on, if this t increases with small t, this accumulates over time. However, we are not, I mean, you have to have a model for rho. Rho depends on the the scale factor. So if you have a scale factor, you can integrate that and find t. So based on that, this frequency shift, you can find that analytically or numerically. And this, as I mentioned, so the background plays an important role here. And these are, before going there, let me see. So yes, so these are the numerical computations. So again, we put mu, here's a small mu, or here's a capital larger mu, just to see what are the effects. So you see that not only the frequency is shifted and the time arrival is shifted, but also we have this shift in the amplitude, change in amplitude. Again, part of that comes from just the time dependence, even in the case of non-polymer systems. Okay, so in this case, the frequency shift leads to the change in the group velocity. You can compute that if you have the function t here, because you can also read it from here. And because of that, again, we have the speed, again, the speed of we have subluminal propagation of the waves. And this difference in the velocity of the waves comes again from the initial momentum of the wave, the mu parameter, basically mu squared here. Again, you have Lorentz violation because it depends on k, actually k squared. And an additional dependence on rho, which comes through dependent of capital T, appears here. So you can actually distinguish if this model actually corresponds to the nature and everything works fine, then you can distinguish the cosmological model of the universe actually from from fitting this to the data. and you will find the form of rho actually. So you can go inverse. Okay, so these are the results that we have. Actually, we have gone. The point is that this is the first step. We wanted to capture basically the first order approximation, something to the full theory. The full theory obviously should have both the background quantized and the foreground quantized. So in this case, we are just considering the classical background and the perturbative or perturbations to be quantized. So that's this is the part that we are actually working on. So let me just summarize quickly. So as I mentioned, we are doing this polymer quantization of the perturbations, gravitational waves on a classical FLRW background. And until now, it was not clear how to quantize the system polymer in a polymer sense, because there's a time-dependent system. It's a time-dependent system. However, we did that, jumping over the phase space and everything, and to resolve this obstacle. The result of that is that not only the waveform, but also the frequency and the speed of the propagations get modified, and also sometimes amplitude, depending on the case. Time dependent or time independent. Also, we have in the case of discrete perturbations, we have Lorentz invariance violation. It's very small, of course, because it goes with mu squared, but anyway, it's present there. And the speed of propagation is subluminal, the speed of smaller than the speed of light, basically, and higher energy waves go slower, basically, compared to the other waves that are lower energy. And as I mentioned, small Lorentz violations are present there. So, so at the present, we are working on 3 related projects that that are like have more priority for us. One of them is the detector arm response for this model. So to see, for example, what happens if you have a merger, black hole merger, what is the change in the waveform of the detector response in the gravitational wave detectors like LIGO. The second one is the studying of the modified power spectrum due to this model, both astrophysical power spectrum and the CMB power spectrum. This is our work in progress. And the third thing, which is probably the most important one, is quantization of the background as well as the perturbations, because that gives us, that is, if this model is true, I mean, polymer quantization is what happens in nature, then we have to have both background and foreground quantized. So yeah, thank you very much. I think I stop here.
Thank you very much for a nice talk. Yes, we still have 5 minutes for questions. Dr. Novak, please.
Yeah. Thank you for the talk. Please, do you have some results, if it's possible to observe it in, for example, DESIGO or BB or observatory? I mean, the gravitation waves. I mean, the signal. I mean.
You mean the amount of this change? Is it? Yeah. Like, this is exactly the work that we are putting this work out probably in 2 months or something like that. So we are computing these changes. We are actually there was a paper I think a couple of months back, which had the gravitational wave with its electromagnetic counterpart. There was one data point, but there was this paper that came out. So that's very valuable for us. We can compare these two and see if we can get some numbers from there. At the moment, I didn't put any numbers here because this is the new work is in progress. So hopefully, maybe in a couple of months, we will have those numbers.
Thank you.
Some more questions?
I have a maybe naive question for you, or maybe I just misunderstood. I thought LIGO did have some statement about the velocity of propagation of gravitational waves being. Am I mistaken about that side? These effects, if they exist, they're much. I would say that we are not sure, but we're expecting to be below the sensitivity of the LIGO for these. So what we are going to do in the new work is that do it backwards. So say that, okay, with this sensitivity, what
parameter mu we need to be to observe, and also find some numbers for the future, like Lisa, so that if with the Lisa sensitivity, if this thing can be observed or not. So.
Thank you.
No problem.
Yes, some more questions, please. I guess that this hand raised by Jan Novak is concerned his question that he already asked. Therefore, let's thank the speaker. Thank you very much.
Thank you.
And our next and the last speaker is Georgi Minich, who already took part in this session. So now it's yours. But please wait, please wait for the 3 more minutes so that everybody could, who is interested, could join us.
Okay, no problem.
Okay, George.
Okay. Thank you, Jerzy. Thank you, Giovanni, for organizing this session on this very important and new and exciting field of science, quantum gravity phenomenology. I will, in this talk, I'll tell you a little bit about the sort of a vision I've been developing with some friends, Lauren Fardell, Rob Lee, and also Jerzy for the last couple of years on just the problem of quantum gravity and quantum space-time in general, and then in particular about quantum gravity phenomenology. So we all excited. We would love, many people, of course, work on trying to understand this leftover problem from the 20th century of unifying these fundamental constants, quantum action, relativity, and of course, relativistic gravity. What has been pointed out by people who have started quantum gravity phenomenology some time ago, like Giovanni and others, is that apart from thinking about the actual models and approaches, we should think about the phenomenological signals. And what we recently, in this very recent paper, is actually Gravitational Research Foundation essay, pointed out with Laurent, Jerzy, and Rob, is that apart from the usual expectation of quantum gravity phenomenology has to do something with the Planck scale, high energy, or maybe some intermediate scales between Planck scale and the observed scale, let's say in high energy physics, etc., that they are actually probes that are associated with the infrared. And I would actually like to say that quantum gravity phenomenology does have an observation, and that's the observation related to dark energy. If you understand it as a cosmological constant, on one side, of course, it's a gravitational object. It's in Einstein's equations. On the other side, if you understand it as a vacuum energy, that's a quantum phenomenon, and therefore it is an obvious quantum gravity observable, except it's probed in sort of astronomical, large-scale ways, not so much as a quantum observable. And this work has been going on, as with Laurent and Rob, for some time. There's even a review today right here. And with Jerzy, we've been also adding sort of components that I think are going more in the direction of quantum gravity phenomenology. Also with some other friends have been working on this dark sector aspects. The main message here is that in some sense, there is something like quantum relativity. At least that's my understanding of what we've been doing, that essentially quantum mechanics has a sort of understanding, you could be understood from the point of view of quantum space-time. It's not a textbook point of view, and there are some new structures associated with it, some unusual geometric structure called bone geometry, some ideas that some of you have been exploring called relative locality in a different context. And that, of course, generalizes to quantum field theory, because quantum field theory is some type of large quantum mechanics. But if you understand it from the point of view of quantum space-time, then there are new predictions, metaparticles. We'll be working with Jerzy and Laurent and Rob, and then metafields, etc. Sort of generalizations of our understanding, or deepening of our, sharpening of our understanding quantum fields, and that we go to quantum gravity and relations to dark matter, dark energy, and dynamical quantum space-time. This is very similar, of course, to happens to classical relativity. We start with special relativity, right? Trying to understand physics of 19th century, electromagnetism, etc., from the geometric point of view. That's how Minkowski geometry, line symmetry, and so forth were discovered. There was a relativity involved there, relativity of simultaneity, etc. And then we generalized, then that was generalized to classical field theory. We teach this in class, and in a quantum context, we understand this representation of Lorentz or Poincare group, particles, antiparticles, etc. And in the dynamical context, classical, we have general relativity. So in quantum mechanics, I just want to remind you of the importance of phases, okay? And this is the simplest possible way of understanding this through ancient wave a particle duality. If you want the duality between particles, geometric optics, and wave optics and wave mechanics, this is what Schrödinger did. Essentially, the analogy between Eichhorn and optics and the action in particle physics, and essentially wave function being the exponent of the action, the same way that the waveforms are exponents of the exponents at the phases, exponents of the Eichhorn. And that was, of course, the sort of quote unquote derivation of the Schrödinger equation by the author himself. Now, the main insight here is that these phases are crucial in the operatorial aspect of quantum mechanics. And let's actually start by defining physics on a lattice. This is very similar to what Eugenia was also discussing, right? And many other people are concerned with this, but where we were going to basically see that the symmetries like Lorentz, etc., are not really deformed. They're there, but present in some form and form. So, okay, if we have a lattice, we have discrete space-time, and this lattice space-time is classical, even though our physics is quantum. And so we could do something, let's say, for example, path integral, define it in some discretized form. And the issue is, of course, when you discretize this, how do you achieve the continuum limit? And there is a procedure normalization, etc., associated with this. Now, as the continuation of this main insight is that in quantum theory, we need a lattice and it's dual. And that's why I was asking Eugenia after his very fine presentation about the existence of this dual. And this is related to some insight that exists in solid state physics made by Zac, which essentially says the following. So if you start with the Heisenberg algebra, but let's say you have a lattice with lattice spacing A, an inverse lattice, then with this spacing 2 pi, h bar of A if you want, then you can define sort of two translation operators. And even though Q and P, the commutator is the canonical Heisenberg-Bohr-Jordan commutator, the U and V's actually commute. And therefore, you should use basically data, right, because they're commuting, that you should be basically labeling your physics both in terms of the eigenvalues of U and V. Now, they don't commute with, for example, things that shift you on the lattice, the number of operators on the lattice and number of operators on dual lattice, but themselves, they commute. Okay, and so this has led some people, I mean, there's a history going to Hermann Weyl and Schwinger and so forth, but in particular Haronov, to rethink sort of foundational quantum mechanics in terms of this, what's called modular variables. So instead of taking a Hermitian, right, you could be taking this unitary complete Hermitian basis, you could take a complete unitary basis, or alternatively define these modular operators, which now have labels, the lattice spacing and the inverse lattice spacing, and they commute. Okay, so that's an interesting thing. It's these modular variables commute exactly how these unitary variables commuted. Okay. All right, so now the interesting thing about these variables is that they're local. They're essentially these holonomies that we heard from Syed. We also, these are these U variables exactly that Eugenia talked about in his talk. Obviously, they have been used with people, by people and in a lot of contexts. They are non-local. They're essentially kind of like some holonomies of Wilson lines, if you want, and they are contextual. They know about this fundamental length. They know about the fundamental lattice spacing, but they're covariant. That's the crucial point, right? So you can actually have modular time and modular energy. Okay, the H bar is now essentially the lattice, if you sense, in the X space, and lattice spacing, if you want, the fundamental energy in the energy momentum space. So they're covariant. So they also capture explicit non-locality, okay, which also has been pointed out, let's say in Eugenia's talk, and other people have mentioned it as well, that if you take something as simple as a Hamiltonian p squared plus v, right? And if you now look at the equations of motion of these modular variables, let's, for example, like this U variable, then you basically get, or if you want as a modular variable, the P variable, which knows about the spacing R, then you get a kind of discretized version of the classical equation of motion, except they're all operatorial. And you see R is essentially contextuality parameter, could be double slit experiment related to interference, etc. So the idea is to reformulate quantum theory using these modular variables, okay? And that because if you really work with space and time variables, that you would call modular space-time. So what does precisely happen mathematically? So you start with the Weil-Heisenberg algebra, which is QP equals IH bar, but U and V are equals 0, the exponents of Q and exponents of P, sort of the complete unitary basis if you want, and they define the commuting subalgebra of Weil-Heisenberg algebra. Now that's a well-defined mathematical object. As a matter of fact, it has been studied, right, in mathematics, and Mackey has proven that the commuting subalgebras of Weil-Heisenberg algebra are actually self-dual lattices that are lifted to Weil-Heisenberg algebra. And this is where the lattice L and the dual lattice L comes in. So if the modular space-time is precisely mathematically this, but it's telling you that apart from classical space-time, there exists this dual space-time. Okay, so this is now a prediction in some sense of this approach, and we have to understand the physics of it and phenomenological implications. So modular space-times in d dimensions then is captured by the symmetries of this structure. First of all, there's a symplectic structure that's associated with the commutators. There is a doubly orthogonal, which is associated with this lattice and double lattice structure. And there you also have to think about how to define a vacuum now, because you have loss translation symmetry, right? You're living on the lattice. And for that, you can introduce the double conformal or double metric. And now you have these three structures with defined, in some sense, board geometry, symplectic, doubly orthogonal, and the double metric, whose intersection actually defines Lorentz. So in some sense, you have a structure in which you have a lattice and a dual lattice, but everything is still consistent with Lorentz. How is this possible? Okay. First of all, this is telling you quantum mechanics in some sense is non-locality that is tied to causality. Causality being essentially embedded in the structure of the Lorentz, and non-locality basically being captured by the fundamental length and fundamental time. And the only possibility that you could say, because you would say like, well, you have a lattice, right? And naively, you know, if I boost, something happens, there's a Lorentz contraction or something, how can that be consistent with Lorentz? Well, the idea here, it's different than the realization that Eugenio was talking about, is essentially that different observers would essentially have different points of view. So that's where relative locality, or if you want observer dependent locality, enters and reconciles fundamental length, or in this one, fundamental non-locality with Lorentz. The statement here would be essentially quantum mechanics could be derived from fundamental non-locality and causality. It kind of emerges from quantum gravity, if you want, cosmological. Anyway, so different observers would probe different space-times, and these are different slices of this quantum or modular space-time with the endowed with Born geometry. And here I'm going to mention a concept that was already mentioned by Eugenio in his talk. In other words, you have a discrete covariant phase space with Brillouin cells. The commuting variables, modular variables, tells you that you can be in the phase cell, but you cannot tell in which one, because the number operators do not commute. And that's why we have Heisenberg uncertainty, right? Because of this non-locality that has to be somehow reconciled with causality, okay? Modular space-time is in some sense discrete covariant phase space that is lifted to this non-commutative Weil-Heisenberg algebra. It's very analogous with what happens to spin. Spin is discrete, but it does not break SO3. And that's due to the superposition principle. So modular space-time is also discrete, right? There's this fundamental length, and there's this dual length of the dual space-time, but it does not break Lorentz, again, because of the superposition principle. So this is what I was talking about in the question period after Eugenio's talk, is that there is this very particular sampling transform, which is called the Zac transform. And essentially what it does is takes the Schrodinger representation, latticizes it in terms of some fundamental like scale, let's say lambda, and then Fourier transform it, but in terms of the dual variables. So then you get a polarization in which both x and x tilde appear. X and x tilde satisfy the Heisenberg algebra. If you do the inverse Zac transform, you find out that the Schrodinger polarization is kind of singular, because you see it knows about discretization. It's spread. So it's not defined locally at x, it's defined at x plus n, and labeled by n, as in the inverse transform. So from this point of view, right, Schrodinger polarization is actually very singular. Okay, so the suggestion would be to use these variables and dual variables. Now, you might be asking what these dual variables mean. And my personal point of view is that essentially they are hidden variables. Okay, they're already present in quantum theory, but they are hidden, but covariant hidden variables, non-local, of course, with respect to X because they don't commute, that capture the issue with measurement problem and choice of basis, etc., etc. Okay, and that's essentially why they are not observed. But the question is how to probe them, and we will discuss that. Anyway, there's some mathematical structure associated. You can write the operators, these variables U and V in a covariant form by exponentiated the generators of symplectic structures, of orthogonal structure, etc. And these would be sort of covariant versions of these modular variables. What do we do in quantum field theory? Well, if you take the free system, you can follow what Dirac did for us, right? You take the Schrödinger representation, right? And then you second quantize, quote unquote, right? It's a formal procedure. It's a misnomer a little bit, but essentially we just treat the size, right, at least for free variables into operators and then follow symmetries and so forth and construct interacting theories. All right. So now the quanta of those operators, of those fields, which are labeled, right, by an index space of X. And that's another way to understand, right, where space-time comes in as a classical variable. There's no T operator in quantum mechanics, right, because if T, there was a commutator of T, whatever, an energy, you could be shifting the energy, therefore there will be no vacuum, old argument of Pauli. Of course, you can do this with modular variables, but there's no operator T, and therefore it's a C variable, right? It's a classical variable. Once we covariantize it, we get a space-time variables, and therefore they serve as an index in quantum field theory. Okay, and their quanta, right, are the particles for which we can write the action with the usual phase space form px dot and Lagrange multiply n for the energy momentum relation p squared plus m squared, and it gives us a classic dispersion relation, and it captures both particles and antiparticles from this point of view. Now, of course, if we wanted to do this on the modular point of view, include the dual variables, where x and x tildes do not commute, and that's where the fundamental length appears, right? We turn them into operators, right? And in principle, we would have to double also the field variables, and therefore we have a double randomization group when we do the continuum limit, etc. The intuition here is that as the way we have x and p, and we have x tilde and a p tilde, once we use symmetries like the gauge symmetry, we shift the p's by the background fields. I'll comment on that a little bit more, and the p will give us the fields, and p tildes would give us, at least from the background point of view, the dual fields. So the first prediction here, apart from the general prediction of the existence of the dual space-time, is that there are quanta of these fields, and they are metaparticles. And that's what we developed with Rob and Jerzy, and now we can generalize this one particle action, and you can see the metaparticle action is completely fixed by this Born geometry structure. There's a non-commutative part captured by symplectic form, which is pp tilde dot. It looks like a Berry phase type term, right? And the overlap, if you want, of a label and the dual label and the derivative of it, right? That's kind of Berry phase-like. That there is one constraint for p squared plus p tilde squared. That's where the double geometry comes in, plus m squared. That should be actually some generalized m. Do not think as a particle m. And then the dual twiddle constraint for this orthogonal, double orthogonal constraint. So in the p tilde goes to 0, mu goes to 0, we get an ordinary limit, we get an ordinary particle. And naively, here it looks like particles associated with d and dual particle mu over e. It's a little bit more subtle than that. You can compute the propagator. You see it looks very singular because there's a delta function of that extra constraint that doesn't exist for particle, pp tilde minus mu, and there's an extra parameter mu, and then over p squared plus p tilde squared plus m squared with the usual prescription, and you can actually derive this consistent with the word line unitarity and causality. Now, in a particular gauge where essentially you go to rest frame of this dual phase space-time, you get this e squared plus mu squared over e squared relation that, even though everything is Lorentz covariant, right? It would naively, in this particular gauge, think of a Lycon gauge in ordinary space-time, gives you something that seems to be a deformed dispersion relation. That's where phenomenology comes in. And in a recent paper, what we've been talking about is taking a curved background, okay? And in that curved background, now you basically, the simplest possible case, you take a some cosmological background, homogeneous isotropic, so you have just a scale factor A, right? And now you can write your dispersion relation as a -2. There is the metric and the inverse metric show up, g mu nu and the inverse of g. So that's where you have e to the minus to p squared plus a squared p tilde squared. If you take this into components, sorry, I didn't write the vectors clearly for the components EP and in tilde p tilde, the vector, you can write these components and think of m tilde m bar as a different mass and mu is an extra parameter that should be constrained by observation. Now there are three Lorentz invariants. You can do new representation theory. You can look at the paper about that. The upshot is the usual mass is related to this m bar squared mass plus one of these invariants, right, which is p tilde squared minus p squared, okay? And the representation theory, there are various cases and so forth. I just indicated two simple cases. It's much more complicated than that. It basically telling you that you have sort of degrees of freedom that kind of toggle, seesaw between each other. Let's say call the visible degrees of freedom associated with the momentum p, and invisible, or if you want to call them dark degrees of freedom associated with p tilde. When a is small, in other words, the early universe, p tilde is very important. But if the universe is large and the late stages of its development, a is large, then p tilde goes to 0. In some sense, these degrees of freedom decouple. They're still there, the sources of energy, right, and mass, but they're still there. And now you can actually, in that context, really talk about this dispersion relation very precisely, okay? So now phenomenology is essentially that we can put a bound, if you want, of that mu. Mu exists for any particle in the Standard Model. In some sense, the Standard Model has a dual, okay? For each field in the Standard Model, there's a dual field. For each particle, there's a dual particle, at least to first order. These particles are somehow correlated into some non-local object, which you would call metaparticles. And if you apply it to neutrinos, we have a bound cosmological on the sum on their masses. As you know, we don't know the individual masses of the neutrinos. We only know the difference squared, right? The masses, we don't know, is it inverted or a normal hierarchy, etc. But we know this from cosmology that the bound is like that. So therefore the mass, the mu for the neutrinos roughly is of the scale which is close to the dark energy scale. That's not surprising because already, right, the difference is squared and the masses are giving you sort of this tantalizing relation of neutrinos to the cosmological constant. Okay, so now we can also compute, if you want, a long-range effect like a static potential. There's a song and dance. The interesting thing here is that it's not Yukawa type, but it has a sort of modulating part. Again, this is known in condensed matter physics, okay, as a Friedel potential, and it's really, really due to the lattice spacing, like the Umplug effect that, in some sense, Eugenia captured. This effect is due to the presence of particles and antiparticles, let's say around the Fermi surface in the condensed matter context. And here it is appearing again in this quantum gravitational context. So if you want to include the background fields, as I said, you basically shift the p's and the p tildes, so that action would, at least from the background point of view, give you, let's say, if you wanted a photon, the usual f squared term, the f tilde term. It looks like a dark photon, except that there is this Berry phase-like term, which definitely would not exist in usual effective field theory, because effective field theory takes lambda goes to 0, and these two guys would be completely decoupled. What will be quantum gravity from this point of view? So we did the quantum mechanics, we did the quantum field theory with implications of objects called metaparticles, that these objects could be actually important for modeling dark matter. In the context of gravity, we just basically have to make all these backgrounds, the symplectic, the doubly orthogonal, and the metric background dynamical. And believe it or not, if you just generalize this, what you did from particle, right, and generalize in such a way so that, let's say, there is a parameter that labels, if you want, the extension of the minimal length, called it sigma, you actually get a bosonic string. It's completely bosonic, it's chiral, and it's non-commutative. So it's not a textbook string theory. The usual string theory appears in some singular limit with basically, you essentially put omega to 0, and then you get something which is called double field theory, rewriting of string theory, etc. But this is completely different than this because it's non-commutative. The background space-time is a modular space-time, not the usual space-time. If you worry about supersymmetry, it would be emergent, so it's not there. It's not really required. The vertex operators becomes representations of Weil Heisenberg, etc. Now, what I point to, because you worry about relative locality, some of you here, an explicit realization of relative locality. So exactly like in relativity, where you can mix x and t, here you can mix x and x tilde. That's done by a background, which essentially it's an anti-symmetric tensor that couples to the string, if you want, world sheet, and you get this non-commutativity in the dual space-time. Okay. Now it's interesting that this background is dual to axioms, which are phenomenologically relevant, because D of B is a 3-form in 4 dimensions that's dual to a pseudoscalar, right? So axioms in some sense here would be embedded in some non-commutativity of those dual space-time. Okay. Now they don't have to be understood as propagating, particles, etc. Now the interesting thing, there's a new non-commutativity, which is now relative locality, where you combine x and x tilde, but a sort of inverse background to B, if you want, beta we call it, and it gives you space-time non-commutativity. And in this particular case, you have a realization of something that people have looked at, right, which is a non-commutativity, fundamental non-commutativity, and they've even put phenobounds on the parameter. This beta AB would be like a theta background that you find in non-commutative field theory literature, except there it's just introduced ab initio. In principle, for varying beta, you also get non-associativity. Right? And that, as you know, it's interesting. Some of you have heard about relations between octonionic structure and the uniqueness of it and the standard model, really of the one that we observe, etc. So in quantum gravity, kind of like in loop quantum gravity, we want, from this point of view, want to build space-time from atoms of this modular space-time, not compactify but extensify. You can also give a matrix version of it, which would be a non-perturbative version, where basically the whole world sheet becomes a modular space. And use those internal variables of the modular world sheet, the dual to tau and sigma, as sort of Fourier transform to the indices of a matrix, and then those x's become matrices, and in some sense you get some matrix quantum theory as a sort of definition, non-perturbative definition of quantum gravity. And about just a little bit about dark energy and dark matter. I think, I don't know, do I have just 5 minutes left or something, or that includes questions? Jerzy?
Yeah, you have exactly 4 minutes to go.
Okay. Okay, so let me mention a little bit more about this dark matter and dark energy connection to this formulation. So as you know, the dark energy and dark matter naturally appear again from the point of view of the Einstein's equations. Lambda naturally, at least lambda over G Newton, parameterizes dark energy, lambda being cosmological constant, and T mu nu kind of splits the energy momentum tensor into visible and the dark. Let's say visible standard model, right, baryonic, and dark is anything that is not the standard model. So the statement here would be the dark would be in the sort of dual, if you want, of the standard model. Now, what about the dark? Okay, so first let's talk about the dark matter and then the dark energy. To leading order in lambda squared, you will be somehow have naive decoupling between matter and then dark matter degrees of freedom. The fields would be doubled, phi and phi tilde. They would depend on x and x tilde. The metric part would be square root of GG tilde now, etc. And if you just naively integrate without worrying about non-commutativity, so this is very naive, okay? If you integrate over the hidden variables x tilde, you will get an effective action that looks like integral square root of minus g, right? Ln of the standard model, and then L tilde that now depends on F tilde degrees of freedom, but they all depend on X. So that would be a dual standard model and dark matter from that point of view. Now, the interesting statement here is that there is some correlation between them because of that lambda. And if you look at actually observations, that this has been a puzzle. Well, this has been observed for 40 years, and you can look at some recent papers I had with Takeuchi and Doug Edmonds about this. Doug Edmonds is an astronomer. Takeuchi is a well-known phenomenologist, particle physics phenomenologist. People have known that there are correlations in some sense between dark matter and visible matter on all sorts of levels, globular clusters, rotational, pressure supported, like elliptical galaxies, galactic clusters, etc., etc. Okay, dwarfs. It's very interesting, and they all essentially, they might have different correlations individually, but they are all correlated across the scales. They go 12 orders of magnitude. And there is this magic number, if you correlate, which essentially some universal acceleration, 10 to the minus 10 meters per second squared. Now, some people in modified gravity and in MOM try to interpret this as a parameter, right, that is somehow indicative of modification of gravity, of inertia, so forth. Here, essentially, it's related to lambda, okay, which is essentially dark energy. And the question is, why is structure relevant for dark energy? And there is some story that we have to tell that you will have to wait a little bit. I think there is some very interesting story about structure formation, connection, structure formation to fundamental physics. But let me give you a sketch of why lambda appears in the first place. Again, let's do the same thing we did the dark matter in the gravitational sector, naively, to leading order lambda squared. So you just double Einstein, Hilbert action, you square g tilde, and you integrate over x tilde. And then you basically get from the integral square root of minus g tilde, you get a g Newton. But from the integral of square root of minus g tilde, r tilde, you get a g Newton minus 1 lambda. So the cosmological constant essentially just arises from the dual sector, the same way the dark matter arises from the dual sector, just if you look at non-gravitational fields. Okay? Now, this dark energy is very interesting because phenomenologically, right, you could write an action that now knows about the volume of dual space-time, replace it by the volume of the observed space-time, and get an Einstein-Hilbert action where L is the Lagrangian that knows about the matter and the dark matter sector, but somehow normalized. This is an action that it's not normalized the usual way. Okay.
Georgia, I need to interrupt. I'm sorry, your time is running out.
Okay. So anyway, I'm just saying that basically the scales between that involve the G Newton and lambda are somehow related with the seesaw formula, which is not unnatural from the point of view of metaparticles, etc. I'm giving you something here, an estimate that essentially involves the why sort of the cosmological constant could be naturally small in this context. In general, is dynamical, etc. I'm not going to talk about other possible things like statistical effects I'm going to mention. Eugenio has been thinking about this in the context of black holes, statistical effects of quantum gravity, new approach to vacuum selection, etc. Anyway, the summary is you can go from quantum mechanics or quantum field theory and quantum gravity based on quantum space-time board geometry, introduce new concepts like metaparticles, metastrings, and so forth, and connect to dark matter and dark energy. And this suggests that there is quantum gravity phenom in the infrared, captured by the different dispersion relation and the static potential as well, the dark matter and dark energy degrees of freedom that come from the dual sector, that they seesaw and they are correlated to each other. Thank you, Eugene. Sorry if I went over time a little bit.
No, you're exactly in time. Thank you, Georgie, for your exciting talk as usual. Jan Novak raised his hand, so please.
So according to you, it's the dark energy is a quantum gravity effect. Okay,
yes.
Am I right? Yeah. Okay.
Yes, it's a quantum gravity effect, definitely. Yeah.
And the second comment, could you somehow quickly say why supersymmetry is emergent when you talked about metaparticles and metafields?
So if you know something about strings, you know that there is a construction of supersymmetry called famous one called quadratic string, in which the chiral matter is realized, right? And there's a unique gauge field called E8, etc., for cancellation of anomalies needed, that starts from a bosonic string. Starts from 26, goes down on a lattice, 16-dimensional lattice, and only then you introduce the fermionic degrees of freedom as sort of some bosonization of the bosonic, chiral bosonic degrees of freedom, and then you basically by fiat project something called GSO projection, so that there is no lowest lying mode which looks tachyonic. Okay, that's essentially how you get a superstring. So the bosonic string, I think, is behind all of string theory. And we knew this for so many years. Why do people insist on supersymmetry? Well, you see, I think that's somewhat historical and somewhat mathematical. First of all, it's a nice mathematical structure if it's not broken, right? And historical is, I think, because of this grand unified, etc. story that we followed since the emergence of the Stator model. But as you know, we do not have any phenomenological indication for this. So now this is maybe explaining, if true, why this doesn't have to be there. Because you see, supersymmetry is a structure that could happen, but it doesn't have to. Okay, it's just a singular structure, right? That it's there, it's natural. But if I were to take from the bosonic string any arbitrary realization in terms of this meta string, non-commutative, so forth, I don't have to have supersymmetry. The other thing that is also telling you, see, for the string, usually cosmological constant is a big problem. As you know, there's a big argument. Is there de Sitter space in string theory? Okay. I do not think there exists unless you have this formulation. You will run into all sorts of problems, similar problems with inflation and so forth. So, okay, that, you know, it's not a theorem, right? But once you have a cosmological constant, it will break SUSY automatically. I mean, that's all, in some sense, always been. There's, at least from the low energy point of view, there's no de Sitter supergravity. It doesn't exist. Okay, so I think this, in some sense, nicely explains that, but you can call it post-diction, not prediction. I hope that that satisfies you. Yeah.
Eugenio, please.
Yes, George, that's fantastic. These infrared phenomenological implications are really intriguing. So I wanted to ask you, I think I understand the modular observables in the one particle sector. That part I could follow easily. My question is, what happens in the what happens to the duality in the n particle sector? And in particular, do you have brilliant zones also for composite particles or only for elementary particles?
Well, I don't know. You know, I don't know what happens with composites. We've been talking about the meta field. I think the crucial thing here is to develop this kind of meta field properly. Okay, and it's a different beast. I mean, you can kind of see this already on the level of the propagator, because the propagator is singular. There's a delta function in it of the what you would call a Diffie constraint, right, over the what you come from the Hamiltonian constraint. So when you write this, if you want to write actions for this thing, it's strange. We have some notes and some wonderings about this, but it definitely looks like a different object than the usual quantum field. Now, one simple thing you could say is like, well, why don't you do representation theory of Born geometry? And that's what we try to do with metaparticles. And even that representation theory, it's weird, okay, because of these two parameters. I mean, you have this m squared and mu, and m is not the ordinary mass. It's sort of, the ordinary mass involves this sort of invariant that you would not usually write, because you have the kind of two invariants. I mean, if you write the list of Casimirs, you have a p squared plus p tilde squared, p tilde, and then p tilde squared minus p squared minus p tilde squared. So you cannot just say like, well, I'm going to pick a gauge p tilde and that's my gauge. Maybe it's natural from the point of view of cosmology, but it's not clear. So the representation theory is complicated. And I think the fields are also very non-trivial. So I cannot tell you anything about the composites, unfortunately. Okay, naively to first order, right? You got this excitation from the background field point of view, and there's other excitations. They're kind of toggling. One is an energy, maybe one is a dual energy. That's mu over E would be your duality, right? And they're somehow entangled. But actually, when you look at it, it's actually one object. It's one object. It's a non-local object. And you can maybe take in from the background point of view, you see a particle and this dual one toggling. But it's kind of like, you know what it is? It's like a zero of this zero mode of the metastring, where there are left modes and the right modes, and kind of left plus right would be X and left minus right would be your dual. Now, usually strings always say like, well, the dual is the same as the ordinary space-time. So you don't worry about it unless it's a compact space and blah, 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 and so forth, right? But even for compact space, we found something new. So, yeah, I mean, non-local objects that look like particles and a dual particle in some limit. That's how these guys look to first order, just as one particle states. I don't know how they look as composites.
So would finding the Casimir for your field theory instead than for the one particle sector help with that? Because then you would just find the dispersion relations directly for the field.
Yes. And that's essentially what we did with representation theory. We didn't publish the whole thing, but it's a little bit involved. But that's you know, if you want to think about metaparticles. But if you want to think about metafields, which I think how we should be thinking, and somehow also, by the way, this is another thing I wanted to point out also for you, is like the UV and IR are mixed. And so for you, I don't know if the same thing happens, that if you take the Brilliant field theory, do the UV and IR mix.
Yeah, and the answer is yes, and in a somewhat surprising way that I was really not expecting. I was surprised. So, for instance, I had the concern that I would get brilliant zones for multi-particle states that would create an immediate phenomenological problem because the Planck momentum is a lot for an elementary particle, but for a composite particle or like a tennis ball is really small. So it turns out that like the identifications are non-trivial, and it's really only for the elementary particle modes one by one that have these periodic identifications. So for multi-particle states, you just get a complicated torus with many periodicities.
Mm-hmm. I mean, the best way for me to think about multi-particle states is you would have to go back to sort of the strength because it has all of them, right? And then, you know, look at operators as representation of this, you know, Weil, Heisenberg, or whatever algebra or Born geometry and so forth. That would be sort of, but I think it's an overkill. One should be able to do this, you know what I'm saying? Kind of like an analogy we would do in field theory, but with this extra structures.
Okay, guys, I think it's time to stop this a very interesting discussion. I don't see any other hands raised. Therefore, I think I can close this session for today. Thank you all very much, and we meet tomorrow at 9:30.
Your
See you
time.
tomorrow.
Impossible time for me.
Well, yeah, it's going to be impossible time for you.
Okay.
Okay, good. See you then.
Thank you, everyone.
Bye.
Thank you. Bye.
Thank you.
Thank you. Bye.